I wonder if it's even worth using them, but not so much. Anyway. All right. So if you happen to have a laptop with you and you got Excel, so if you got Microsoft stuff on it, Office, you could follow along with when we get to that portion. But a little bit before that, what we're going to be talking about is numerical methods of approximating solutions. So starting in section 2.4. So if we are given an initial value problem, which I will be just referring to as IVP for now on, initial value problem.
In this frame, I think it's
Right, that lamp, is it just washing about?
It wasn't a pen, it was the absolute.
Yeah, okay. Well, is that better? Yeah, no, I don't. Yeah, maybe I bumped that and turned it back on. I wasn't doing that earlier. So if we have an initial value problem, dy dx equals, and some expression involving x and y, or potentially just one of them. Okay? So potentially a function of two variables, but it also could just be a function of either x or y. But what's important is that it's a first order. If it's a first order, in other words, if it meets the same criteria to create a slope field, right? A first order equation where I have dy dx equals some expression. So in other words, if I can create a slope field for this, we can also take advantage of some numerical methods of approximating it. And say the initial condition y of some value x naught, not necessarily 0 or anything like that, but we have some initial condition y of x naught equals y naught. In other words, the point x naught comma y naught is on the solution curve. So that's just a particular point that it has to satisfy. Now, we may not be able to solve this, and we do have methods to solve first order differential equations. If it's separable, if it's linear, things like that. Okay? But if it's impossible or very difficult to solve, then we can use the numerical methods. All right, so we may not be able to find the exact solution, or maybe it's prohibitively difficult. In this case, we turn to approximation technique. Oops. What I call an indirect method. So you could use a slope field to generate a slope field for the solution curves, and then if you do know an initial condition, you can drop that in there and see what the curve looks like. But that doesn't help you know what particular values are. Okay? So we must turn to an approximation method. And the first one, and I think the only one we're going to be really looking at, is Euler's method. Yeah. So Euler's method. So if you took Calc 3 here at PCC, that's part of the stuff that you look at as an intro into differential equations. I know at PSU they don't have that requirement. Although I just heard they're going to be reinstating the Calc 3 requirement to go on, even for engineering. So before you take Calc 4. Anyway, so the idea behind it, say here's the solution curve, which again, we are assuming we don't know. So this is y of x, this is the exact solution. Which we're not assuming we know. But we do know a particular point on it, They're saying that, okay, what if I know that it satisfies the initial condition y of x naught equals y naught? So this is that point. Okay. Well, if I know a particular point, then I can plug those points in and calculate what dy dx is at that instant, right? Because the first order differential equation tells you about the slope of the tangent line of the solution curve at a particular point. So if I do know a particular point, I can plug that into that function and it'll tell me exactly what dy dx is here. And that's just the slope of the tangent line. So the idea behind Euler's method is that, okay, if I know a single point that is on the exact solution curve, I can calculate the tangent line, or the slope of the tangent line at that point. Okay? The idea is I can follow the slope of that tangent line a certain distance. Say this is the point. I could follow that tangent line a certain distance and find another point, x1, y1. Now, it probably wouldn't be on the curve because we are essentially linearizing the function and following it a short distance to find an approximate point that we think would be on the curve, x1, y1. Okay? So right here, this slope follows this, dy dx equals f of x naught, y naught. Okay, the slope at that point. So that's the slope of the tangent line. Well, we can use this method. Now, this distance out here that we decide to go horizontally, so we follow that tangent line for a short distance and calculate a y value. Okay? And the idea is that that distance is very short, then that point, x1, y1, will be very close to a point on the solution curve, yeah? So this distance right here, horizontal, call this delta x, or what we call h. Delta x, okay? So I know that from that point, just using the equation of a slope, slope of the tangent line would be y1 minus y naught over x1 minus x naught. Right? Rearranging that a little bit, solving it for multiplying both sides by x1 minus x naught, we get y1 minus y naught equals slope of the tangent line times x1 minus x naught. If we stop at that point, that looks a whole lot like the point slope form of a line. Okay? But let's solve this for y1. y1 equals y naught plus, and slope of the tangent line, that is dy dx, and given by this expression, okay, f of xy. And this little distance, x1 minus x naught, that's delta x, or h. All right, so y1 equals y naught. So knowing a particular value that's on the curve, I can estimate the next one by taking the previous y value plus, and this expression represents the slope of the tangent line at that point, times h. Oops, usually we write the h in front. Let me do that. So y1 is y naught plus h times f of x naught y naught. Okay. So what that does is, yeah, we go from this point, some little distance, we follow that tangent line, some little distance h, calculate a new y1. That's an approximation for a point on the curve. we get to that point y1, x1, y1, we recalculate the slope. In other words, what the slope of the tangent line would be at that point. We follow that tangent line again, the same distance, delta x or h, and recalculate y2. We find a value y2 that's going to be very close to the exact curve. Okay? We stop there, we recalculate the slope of the tangent line at that instant, go off again a small distance away. Okay? And so this is an iterative technique. And if I know y1, then I can find another point. y2 is the previous y value plus that delta x, or step size, times f of x1, y1.
So on and so on.
And so forth. y3 is going to be the previous y value, y2, plus some same step size, we keep that constant, times f of x2, y2. And so on. And the general step, this is an iterative process, to find an nth value in that process. Y sub n is going to be the previous y value, y sub n minus 1, plus h times f of evaluated x sub n minus 1, y sub n minus 1. All right, so some of you may remember this. That's the general. Okay, so it's an iterative technique. Now, as you can see, right, there's going to be some error involved, because if I go some distance along the tangent line, I probably won't land on the exact solution curve. I find my y0, recalculate the slope of the tangent line there, and go off in the slope field at that slope some small distance again. So there's going to be some error involved. That's why this is an approximation technique. But the idea is, if h is very small, then I'm going a tiny little distance, calculating my next y value, and it's going to be very close to the curve. So dy dx will be very close to the slope of the actual solution curve. Go off again in that distance, in that direction, a tiny distance. Okay? So the smaller h is, the better. Stay close to the actual solution. So let's just see this in action.
Is there any way to take h to infinity?
Would that be integrated?
Yeah. I guess what we can't do.
If you could find an iterative formula for f. Yeah.
Step size is infinity, that
No,
just
no,
like,
no. I meant take it to, I guess, to 0 rather.
oh,
Not to make as many Lego alignments on eventually.
So this is an iterative technique, to estimate. So these are not going to give you exact values. The only exact value I know is the initial condition, f of x naught equals y naught, or y of x naught equals y naught. We know that one to be true. And to estimate, we estimate the next y value using a constant step size. H. Okay? So say, there's my x-axis. Just for the sake of being different, say the actual solution curve is concave down in this instance. So say this is the exact solution curve. If I do know some initial condition, f of x naught equals y naught, so if I know this point is on a curve, x naught, y naught. Okay? We follow some fixed distance. We follow the tangent line calculated at this point, the slope of the tangent line. So we follow that tangent line a certain prescribed distance, right there, and we calculate a new point. That would be x1, that's gonna be, that distance is set, it's gonna be constant. And there's my y1. Okay? Now, we do the same thing. At this point, at x1, y1, we stop, we recalculate what the slope gives us using the first order differential equation. And we go that same distance, delta x, in that direction and calculate an x2. Well, x2 won't so much be calculated, that's going to be very predictable. Constant step size h in between these. And there's my y2, okay, et cetera, et cetera. Okay, so we'll get this approximate solution curve. And you can see, well, if the exact function curves very fast, then the Euler's method can get away from it. All right, so we want to keep the step size small. Okay, let's do an example. We're going to do one. So say we're given dy dx equals 2y minus 1 with the initial condition y of 0 equals 1. Okay? So that's my x naught, that's my y naught starting points. All right? And this, notice, this is doesn't involve x. What kind of equation? What is it called when the independent variable is missing? What was that? Autonomous. Right. So this is my expression. Now, watch your eyes carefully. This is my little f of x comma y. It's just that x is absent, regardless of what x is. It's totally independent of x. Doesn't matter. So, first, you might note that this can be solved exactly. This is an example of one that can be solved exactly. Now, in the intro to this, I said, when you can't, find an exact solution, you can use Euler's method. Well, Euler's method can be used on any first order that can be isolated for dy dx. So in this example, we can find an exact solution curve. And I want to do this one because I want to compare the exact with what we get when we do Euler's approximation question. Yeah.
So if you can't solve it, how is there any way to tell how far you're off if you can't solve
That's
it?
a good question.
So like, let's say you're estimating and you're down. How far How do you know how far you're off of what it should be solved for if you can't even solve it to begin with?
So Euler's method, I'll just say this, for certain functions, it is very poor.
Yeah.
If the actual solution curve, for instance, has a vertical asymptote, Euler's method will probably skip right over that asymptote, right? It will launch you, and you'll get some other stuff on the other side of it. It won't know that there's an asymptote there. It'll give you maybe a real steep tangent line, but then if you follow that tangent line over delta x, maybe you skip over that.
But a lot of it depends on how small your step size is.
Yes. But even if it's very small, it won't go.
It's not gonna
it won't
Eventually
perform
skip
well.
over the asymptote anyway. Like
Yeah,
you
it
are
probably would. It probably won't perform well, and that depends on the second derivative of the exact solution curve. If the second derivative is very large, in other words, if it's curving very quickly, Euler's method will always be lagging behind. It will give you big errors in each term because you're linearizing it at each step. Whereas if the second derivative or the curvature of this function is very large at a point, Euler's method is going to be lagging behind. It's not going to follow that curve very, very nicely. So there is a discussion about it in the book. There's a whole section on examining Euler's method. It says taking a closer look, and it talks about how it's pretty crude and there are better methods.
Find f of x and y, is it just dy dx?
This?
Yeah.
Oh, dy dx, just some expression. So that f of xy is just some expression involving x and y, or possibly just one of them. So that little f is just a name for this expression on the right side of the equation, that's all. Okay, so first off, we're going to solve this exactly. So one thing to note about this, and this will be a good review. I can write this dy dx minus 2y equals -1. And this would be what type of first order equation? So there, you can actually do it by separation of variables. If you've got the whole 2y minus 1 down in the denominator, dx on the other side, you can actually do it by separation of variables. I'm going to do it this way just to remind you of the integration factor. Okay? So we're going to use this integrating factor. E to the, oh, and that's the p of x function in front of the y. So the function times y, it's e to the integral -2 dx. All right, so what do we get there? Yeah, just e to the -2x. Multiply both sides of the equation by this. That gives us the equivalent equation e to the -2x dy dx minus, and I'm going to put that 2 in front and multiply this term by e to the -2x, and you might recognize that this looks a lot like a derivative on the left. And on the right hand side, I need to multiply e to the -2x, so I get negative e to the -2x, right? Okay. So this is the result of a product rule. And this is the derivative with respect to x of what?
Yeah,
-2x times y.
E to the -2x times y equals -e to the -2x. So we integrate both sides. Imagine, bring that dx, I'm integrating, well, this is derivative with respect to x, so when I integrate that, both sides, we just get e to the -2x times y equals, integrate this. Where's my red integrating pen? All right.
So I have a question.
Yeah.
Where does that dx for the other side come from?
This is the result of differentiating with respect to x.
Not that side, the other side. We just
Where does the
kinda-
dx come from?
We just kind of pop one in.
Imagine that guy going over there.
Oh, and
Yeah, since this is the result of differentiating with respect to x, that has to be the result of differentiating with respect to the same variable x. So it makes sense to integrate with respect to x.
okay.
Yeah. So we get e to the -2x, but what's my guy down here? 1/2. I was thinking reverse. When I differentiate this, that -2 has to knock out that number out front and leave a -1. So it doesn't, yeah, so it's just positive 1/2 out front. Okay. Plus constant, good. All right, solving this for y, and dealing with these negative exponents, imagine multiplying both sides by e to the positive 2x. E to the positive 2x. So I'd have 1/2, and imagine e to the 2x multiplied by this, it would knock that out. And then I'd have plus c e to the 2x. Okay? You get the same thing if you divided both sides by e to the -2x. C divided by e to the -2x, flip it back up, make the sign positive. Okay. Now we could use the initial condition. And the initial condition was y0 equals 1. So put in 0 for x. E to the 0 is 1. I get 1/2 plus c. Must equal 1. And that allows me to solve for c pretty easily, right? C equals 1/2 again. All right, so y of x equals, and c is 1/2.
Back about 1/2.
1/2 plus, oh yeah, 1/2 e to the 2x, and yeah,
You just leave it in there. Doesn't matter.
yeah, I could factor out that 1/2, and I get 1 plus e to the 2x. Okay, so that's not so bad. All right. So we do have an exact solution. We're just going to use that to compare in a moment what we get. So part B, we are going to use a step size of 0.1. Okay? To estimate, and this is numerical, we're going to estimate y at 0.5. Okay, so we got to go through a few iterations. Starting at 0, 0, 1 is our first point. We need to run through that iteration until we hit x being 0.5 and find out what the y value is. Okay, so we know that y of 0 equals 1. That's my first value. Now, y of 1 equals, I'm going to write down the formula, y sub 0 plus step size times f of x naught comma y naught. All right. So putting these values in here, I get 1 plus, and h is going to be a constant at, we're calling it 0, we're using 0.1 here. And f evaluated at 0, 1 gives you what? 0, 1, for 0 for x, 1 for y, I get 2 times 1 minus 1. Okay, so that gives me 1 plus 0.1 times 1, we get 1.1. So that's my first calculated, my next y value. And what I do is just to, so I know where I'm at in the process, we went from y0 to y1. We're using a step size of 0.1. So at my initial point was 0, 1. That's x naught, that's y naught. So the point I generated here, going one step size in x, that's corresponding to 0.1, and the y value, 1.1. So that's my x1, y1. Okay? Now y sub 2 is going to be equal to y sub 1, which is the previous calculated value, plus step size times, and I'll write this in here, f evaluated at x1, y1. Now, calculator is very handy. Oh man, I didn't bring my TI either. That's all right. You want one?
How's one?
The magic is moving.
That looks slow.
All right, so escape, clear, where do I want them? There we go. All right, so I got 1.1 plus step size, that's 0.1, times, and f, this is just the differential equation, the right side of it, evaluated at 0.1 comma 1.1. Well, what value do we get from that if you put in 1.1 into that? It was 2y minus 1, and the y value we're using is 1.1, right? 1.1 minus 1. And we get 1.22.